You know, there's something I find absolutely remarkable about gravity. It's the most obvious force in the world. You drop something, it falls. Simple. Everyone knows this. A child knows this. And yet when you really think about what's happening, when you ask why things fall, you discover something so strange, so beautiful, that it changes everything. Let me tell you what gravity actually is. Not the name, not the word, but what it does, what it means. Every object in the universe pulls on every other object. The earth pulls on you. You pull on the earth. The moon pulls on the oceans. The sun pulls on the planets. Right now, as you're sitting there, you're pulling on everything around you. The walls, the furniture, the air, everything. And they're pulling back. The force is tiny, unbelievably tiny for ordinary objects. Between you and the person next to you, the gravitational attraction is so small that you'd need incredibly sensitive instruments to detect it. But it's there. It's real. It never stops. Now here's the pattern Newton discovered. The force depends on two things: mass and distance. The more massive the objects, the stronger the pull. The farther apart they are, the weaker the force. And the relationship is precise. Double the distance, and the force becomes 1/4 as strong. Triple the distance, 1/9 as strong. It follows an exact mathematical rule: 1 over the distance squared. This is extraordinary. Think about what it means. The same rule that makes an apple fall from a tree also keeps the moon in orbit around the earth. The same force, the same mathematics. Newton figured this out by asking a simple question. If gravity makes things fall, what if it reaches all the way to the moon? The moon is falling. Right now, it's falling toward the earth constantly, but it's also moving sideways very fast. So as it falls, the earth curves away beneath it. The moon keeps missing the earth. That's an orbit, falling and missing forever. And here's what makes this beautiful. You can calculate exactly how fast the moon must be moving to maintain its orbit. You can predict where it will be years from now, centuries from now, and the predictions work. The mathematics matches reality perfectly. The same applies to planets orbiting the sun: Mars, Jupiter, Saturn, all of them following this one simple rule. Gravity pulls them toward the sun. Their sideways motion keeps them in orbit. The balance between falling and moving sideways creates stable paths that last for billions of years. But here's something that puzzled Newton himself. How does gravity work? The sun is millions of miles from Earth. How does it reach across all that empty space and pull? There's nothing between them. No rope, no physical connection, just emptiness. And yet the force is there. Newton didn't know. He admitted it openly. He said the mathematics describes what happens, but he couldn't explain the mechanism. How does one object affect another object far away? He called it action at a distance, and it bothered him deeply. For more than 200 years, that's where things stood. Gravity works. We can calculate it. We can predict it, but we don't understand it. Not really. Then Einstein changed everything. Einstein said gravity isn't a force at all, not in the way we usually think of forces. There's no invisible rope pulling objects together. Instead, mass bends space itself, and objects move through that curved space. Imagine a trampoline. Put a heavy ball in the middle. The trampoline surface curves down around the ball. Now roll a smaller ball across the surface. It curves toward the heavy ball, not because the heavy ball is pulling it, but because the surface itself is curved. The small ball is just following the shape of the space it's in. That's what gravity is. Mass curves space and time. We call it spacetime because they're connected, woven together into a single fabric. And when space-time is curved, objects naturally move along curved paths. They're not being pulled. They're following the geometry. Near Earth, space-time is curved just a little bit. That curvature is what we feel as gravity. Near the sun, the curvature is stronger. Near a black hole, space-time curves so severely that nothing, not even light, can escape. And here's the beautiful part. Einstein's picture explains something Newton's couldn't. If gravity is curvature, then changes in mass create ripples in space-time, gravitational waves. Two black holes orbiting each other, spiraling closer and closer, create waves that spread out through space at the speed of light. We've detected these waves. We've measured them. Einstein was right. But let me go back to something more basic. Why do all objects fall at the same rate? Drop a feather and a hammer in a vacuum, and they hit the ground at the same time. Why? In Newton's picture, this seems like a coincidence. Heavier objects experience more gravitational force, but they also have more inertia, more resistance to acceleration. These two effects exactly cancel. Every object accelerates downward at the same rate, regardless of its mass. In Einstein's picture, there's no coincidence at all. Objects aren't being pulled. They're following the curved spacetime, and the curvature doesn't care what the object is made of. A feather and a hammer follow the same path through curved space because the path is determined by the geometry, not by the object. This was tested on the moon. An astronaut dropped a hammer and a feather. No air resistance. They fell together, side by side, hitting the surface at the same instant, exactly as Einstein's theory predicts. Now, gravity is weak, incredibly weak compared to other forces. The electrical force between charged particles is about 1 billion times stronger than gravity. When you pick up a ball, you're fighting the gravitational pull of the entire Earth, and you win easily. That's how weak gravity is. So why does gravity matter? Why does it dominate on large scales? Because gravity is always attractive. It always pulls, never pushes, and it doesn't cancel out. Every bit of mass adds to the total gravitational pull. In a planet or a star, you have enormous amounts of mass all pulling together in the same direction. The effect adds up. Electrical forces are different. Positive and negative charges attract, but positive repels. Positive and negative repels negative. In ordinary matter, the positive and negative charges are almost perfectly balanced. They cancel out. What's left is just gravity. That's why gravity shapes the universe. It pulls gas clouds together to form stars. It holds galaxies together. It determines the structure of space-time itself. The universe is full of mass, and all that mass is pulling on all the other mass. Gravity is the force that builds cosmic structure, and it all follows from one simple pattern. Every mass attracts every other mass. The force depends on the masses and the distance between them. 1 over distance squared. That's it. That's the law of gravitation. Newton discovered the pattern. Einstein discovered what it means, and we're still learning. Gravity waves, black holes, the expansion of the universe, dark matter, all of it traces back to this one force. This one relationship between mass and space. You know what strikes me most about gravity? It's everywhere. Constant, reliable. You can trust it. Drop something, it falls. Always. The mathematics works. The predictions match. And yet, the deeper you look, the stranger it becomes. Space curving, time bending, objects following paths through a geometry we can't see. The universe doesn't owe us explanations that fit our intuition. Gravity just is. We've learned to describe it. We've learned to calculate it. We've learned to use it. But the question of why mass curves space-time, why this force exists at all, that's still open, still waiting. And I think that's wonderful.